everyone. I'd like to thank you for attending this webinar. The title of this webinar is GPR and Applied Geophysics Principles, Applications, and New Trends. Before I go on the technical, just would like to introduce myself briefly. My name is Hesham El-Kaliouby. I'm Egyptian. I got my bachelor degree from Cairo University a long time ago in '87, and then I got a diploma in computer science from Cairo University as well in '90. And then I got my master's degree in geophysics in 1995. And then I got my PhD from the University of Arizona in the US through a joint program between Egypt and the US back in 2001. Then I got a postdoc at the same university, but in hydrology and water resources, University of Arizona, through a Fulbright grant. Then I worked as an associate professor in King Abdulaziz University in Saudi Arabia. And after that, I worked as senior research associate in Lancaster University in England, in the UK. Then I worked as a consultant, geophysical consultant for the Saudi Geological Survey in Saudi Arabia. And after that, I returned back again for teaching in Sultan Qaboos University in Oman from 12 to 16. And then I returned back home as a professor at the National Research Center of Egypt till date. From 2014 till date. I also was a visiting professor for Central South University in China in the last couple of years. My research interests are broad. I work in near surface applied geophysics, hydrogeophysics, mineral exploration, environmental engineering geophysics, the techniques I'm interested in are mainly electrical, electromagnetic, GPR. I also do a lot of work in forward and inverse modeling. All of my publications are posted in Google Scholar, ResearchGate, Academia, ORCID, Scopus. You can download all my papers from there. I've been teaching in several universities in Saudi Arabia, in UK, in USA, and in Oman as well. I did a lot of teaching, including basic and advanced courses in geophysics, particularly electrical and electromagnetic methods courses, I mean. During my work in Sultan Qaboos University, I was supervising the student chapter there, the EAGE student chapter there. And fortunately, we got the second best student chapter in 2014, 2015 across the whole world. And this was a good honor for myself and the students of the chapter at that time. I was also elected as the first EAGE lecturer in Africa, where we did a student lecture tour in many African countries, including Egypt and Nigeria. The course was titled The Electromagnetic Methods for Near Surface Geophysics. That was in 2017. And I got an award from the EAGE that time for this lecture tour I did in Africa. And it was a good honor for me. After that, I was also selected as the honorary lecturer for the SEG, for the Middle East and Africa. And also I did an online lecture about the induced polarization effect in time domain electromagnetic prospecting. That was in 2019. The tour was virtual, online, like this one, and attended by many students and professionals across the world. And I also got an honor. It was honored during the SEG meeting 2019 by the SEG president at that time. This was the honorary ceremony, or the honor and awards ceremony, and I got an award for teaching this course in 2019. These are some photos for the EAGE and SEG lecture tour did in Africa in 2017, 2019, particularly in Nigeria. I also did a similar tour in China for about 6 universities in China, and I also got a distinguished lecture award from the China International Geoelectromagnetic Workshop 2023. And it was a great honor to visit these prestigious universities in China. About today's lecture, which is about GPR, I'm going to talk mainly about the principles, applications, and new trends of GPR. And at the end of my lecture or the webinar, I'm going to give the application, a case study about cavity and sinkhole detection using GPR, and finally the conclusion. This is the outline of today's webinar. Generally, for any geophysical method, they have a source that puts some energy into the ground, whether this source is natural or artificial, put some energy in the ground. The idea is to do a perturbation or a change in the physical properties of the subsurface. And then we measure this change by different sensors. and got some data. We process this data and filter it, and then try to interpret this data to estimate what's in the subsurface that caused these measured data. This is in general for any geophysical method. Talking about electrical and electromagnetic methods, this plot here shows a frequency versus depth. As you all know that there's an inverse relationship between the frequency and depth. Many geophysical methods use a broad or different frequencies from as low as millihertz up to mega and gigahertz range. The higher the frequency, the shallower the depth of investigation, and the lower the frequency, the deeper of the depth of investigation. So, for example, for magnetoelectric method that uses very low frequencies from millihertz up to a few hertz, it can go quite deep, hundreds of meters, thousands of meters, and can go to the core of the Earth. Actually, it can go quite deep into the Earth, very deep depths. For method like induced polarization and resistivity, these techniques works in the hertz range, and they can go from go in depth from a few meters up to hundreds and maybe a few thousands of meters. Transient electromagnetic or time domain electromagnetic works in a bit higher frequency, kilohertz range, and can go also from a few meters up to hundreds of meters, and sometimes could reach to about 1,000 meters, 1 kilometer in depth. For today's lecture, GPR falls in the extreme high frequency geophysical method. It works from the mega to gigahertz range, and as a result, it can go in a near surface, very shallow, from a few centimeters actually to a few tens of meters. So this falls in the near surface geophysics. So what's important about near surface? Why we are interested in studying the near surface? Actually, near surface contains a lot of mineral resources, water resources. It can also be useful for geotechnical and engineering studies like constructions, foundations, tunnels, utilities. All of these stuff are in the near surface. It can also be, we can also interested in near surface studying environmental studies like groundwater pollution, seawater intrusion, chemical and hydrocarbon leakage, also in landmines, unexploded ordnance, buried bodies, landfills. All of these are in the near surface. One of the most important applications for GPR is archaeological studies, because GPR is very useful in detecting archaeological studies, because it falls also near surface, and also important GPR can go in archaeological sites without doing any change in the site. GPR historically, the word radar itself means radio detection and ranging, and the idea started during the World War II, when they was trying to find the airplanes in the air. So they use the antenna to send a signal that could hit in the airplane and turn back again. Knowing the two-way time and knowing the velocity of the electromagnetic waves in air, you can find the distance. How far is this airplane coming towards us, and how big also is the airplane from sending many pulses. Then after the World War II, they started to use the same concept for civilian applications. So the same idea, we have a transmitter that we send a signal into the Earth. Some part of this signal got diffracted, and other part is reflected back into the receiver antenna. From the received signal, we can analyze and try to determine how deep is this target, how big or how small it is, can know dimensions and depths of this target. However, it's more complicated because the Earth is very heterogeneous, unlike the air, which is very homogeneous. So we can have some challenges to calculate the velocity to determine how deep is the target. But it can provide us with very high resolution, since it's using high frequencies to determine the dimensions of the subsurface target. Actually, GPR is quite similar to the Echo Founder. You know, the Echo Founder for the seas, when they would like to determine if there's any fish, or determine the sea floor or the bottom of the lake, how deep it is. So basically, in the sounder or the sonar, they send a signal or a pulse. This pulse is scattered or reflected from the fish in the water, in the sea, or reflected from the sea bottom or sea floor. And as you go on, the boat moves, collects many recordings from these reflections coming from the fishes and from the sea floor. And they can display this recording side by side in what's called echogram, and you can see it right here, which shows the fishes and the sea floor. This is quite similar to exactly what the GPR is doing. In GPR also we send signal in the subsurface and we get some reflections that tells us about these targets, whether it's a cavity or utilities or any target in subsurface. So we have a signal, send the signal to the subsurface and get some reflections, and based on these reflections we can determine what's exactly in the subsurface. So similar to this echogram, we have what's called radargram in GPR. And as you can see, for this radargram, there are some reflections very strong and some reflections are much weaker. So these reflections being strong or weak depends on the contrast in the physical properties of the subsurface. Basically, there are 4 physical parameters that control these contrasts in this subsurface. So are mainly called the electric permittivity, electric conductivity, magnetic stability, and the frequency. These 4 parameters controls the contrast in subsurface. Permittivity actually controls the velocity of propagation and reflectivity. Frequency, the effect or controls the depth of investigation and resolution. When I say a word resolution, it means how detailed, like for example, high definition, how high or how low is the details we can see from a subsurface. Conductivity, electric conductivity affect the depth of investigation, as well as the magnetic permeability affects the depth of investigation. I'll go through all of these parameters in some details in the following slides. So let's start with the first one, which is the permittivity, electric permittivity. The velocity of the GPR or electromagnetic is inversely proportional with the square root of the permittivity, epsilon or epsilon r as a relative that permittivity relative to the vacuum. And the range of this permittivity from 1 to 80. The minimum is 1, smallest one is 1, and the highest is 80. 1 corresponds to air or vacuum, and the velocity of GPR in air and vacuum is about 0.3 meter per nanosecond. While for the fresh water or saline, for water in general, it's about 80, and the velocity in water is about 0.03 meter per nanosecond. Most of the other earth materials like granite, limestone, salt, ice, all of this stuff have a very small value that range from 3 to 8, a very small permittivity. And this also have a reflection on the velocity of the subsurface, of the material subsurface. Basically, the permittivity can be defined as a measure of the capacity of the subsurface material to store energy when we have an applied electric field. So if we have an atom like this one that's in electrical equilibrium before applying electric field, when we apply electric field, what happens is that the electrons try to escape out of this atom, but the attraction force from the nucleus, from the protons here, is very strong since it is a dielectric. So very strong attraction. So what happened is that we get a displacement. The electron just get displaced when what's called displacement current. It's displaced, and after the removal of the electric field, just return back again to the equilibrium position. So permittivity can be defined as a measure of the material's ability to hold and pass the charges. So it acts like a capacitor, for example. So it is very high for water and very low for the air. For example, here, if you put a GPR antenna above air, which could be like a cavity, for example, so it moves very fast. Remember that while in water, it goes very, very slow. Remember that there's an inverse relationship between the velocity and permittivity. So in water, it goes very, very slow, while in air, it goes very fast. GPR could be best used when we have a dry sand conditions or we have an ice or snow. It works very well. While it's not very good when we have a wet clay or any conductive material in the electric conductive material in the subsurface. So in order to see the different subsurface materials, we need a contrast in the electric properties to be able to see this interface with the contrast between the different earth materials. To measure this reflection or contrast, we use a reflection coefficient R, which shows the different in permittivities between the different media. Of course, when we have a high reflection coefficient, then we can see clearly. We have a high contrast. When we don't have a small reflection coefficient, then we cannot discriminate between the materials easily. For example, here, If we have a dry sand over a wet sand, dry sand permittivity is from 3 to 5. Wet sand is about 20 to 30. Then we have here a large reflection coefficient. It's similar to a condition when we have a water aquifer or a dry zone, and then we have a water aquifer, for example, wet sand. Then we have a big contrast between the permittivities, and we can see very easily. On the other hand, if we have like dry sand and underlain by granite, despite they are two different geological material, but the permittivity is quite close. For dry sands, like 3 to 5, granite is 4 to 6. The contrast here is very small reflection coefficient. So we cannot discriminate them easily using GPR. The second physical property, which is magnetic permeability, it is measured by the, it just shows us how strong is the magnetization of this material, how magnetizable is material. So it's measured by the susceptibility, magnetic susceptibility or permeability. So in general, high magnetic materials, for example, like hematite, like basalt, like magnetite, ilmenite, all of these highly magnetic materials are not a good environment with GPR. Actually, will cause high attenuation for GPR. So it's not recommended to conduct GPR above highly magnetic materials. For the third parameter, which is electrical conductivity, basically conductivity can be defined as the ability of material to conduct electric current in the presence of an applied electric field. High conductivity is usually associated with saline water, for a lot of ions in the water, highly saline water, or the presence of clay content. This will increase the conductivity. Of course, if we have mineralization, also it will increase the conductivity. So highly conductive materials, again, is not a good environment for GPR to be cause high attenuation from GPR signals. Materials which have like more than 0.01 Siemens per meter is not a good for GPR. It's difficult for GPR. For example, air, dry granite, sand, gravel, limestone, concrete, fresh water, asphalt, all of these are low conductivity materials. Very good for GPR. GPR can work in this environment easily and can go quite deep through these materials. On the other hand, wet clay, shale, silt, seawater, minerals, all of these materials have a high conductivity, high electric conductivity, so it's poor for GPR. So it cannot go them easily, have a low penetration depth within these materials. It's important to know the limitations of the technique, when I should use it and when I should not use it. This is an example when we have, for example, a dry granite, and the other one is wet clay. Let's see how GPR can go through dry granite. Then the dryness here will cause a fast movement for the GPR, and the granite is resistive, not very conductive, allowed to go quite deep. Wet clay, the wetness here will slow down the movement of the GPR pulses or signals as it go on. And the presence of clay, since it's a conductive material, will limit the depth of penetration, cannot go quite deep, will limit the depth of penetration. While we have a granite, it can go quite deep into the granite with a fast. So it's important to know how the GPR can penetrate through different earth materials. Attenuation is a very important parameter. It tells us which parameters can cause attenuation for the GPR signal. So it indicates how much a signal is dissipated or decayed when it moves into this material. Three main parameters that affect the attenuation: the frequency, magnetic permeability, electric conductivity. Any increase of the frequency or magnetic permeability or conductivity will cause a high attenuation, will have caused attenuation to be very high. For example, if we have a highly conductive material, like we call it high loss or lossy media, like mineralization or wet clays, this will cause a high attenuation because it will increase the attenuation factor. If we have a high resistivity material, then it is not a problem for GPR. Of course, we have a sigma equals 0, which is pure propagation. Alpha will equal 0. This is happen in vacuum or space, actually. So this is an example. If we have a 1 millisiemens materials, this is a resistive material. So this is a GPR signal. We have a target here to reflect, and the reflection is very strong. So this will go to the receiver antenna, can be detected easily. On the other hand, if we have a more conductive material, like 5 millisiemens per centimeter, again, this signal for the GPR will go down. But when we have a reflection, the reflection magnitude is weaker than the first one, so it can be challenging to detect. If we have a more conductive material, like 25 millisiemens per meter, then still we have you can see the signal is attenuating even before it goes to the target itself. So the reflection is almost no reflection. It's impossible to detect. So the higher the conductivity, it's harder to detect these targets. So it's important to know the limitation and when I should use GPR, when I should not use it. This is a comparison for different conductive materials. The table here shows the electric conductivity and the corresponding attenuation factor, alpha. For different earth material, for example, for air, if we have fresh water, fresh water is resistive, it's electrically resistive, like 0.01 millisiemens per meter. And as a result, the corresponding attenuation factor alpha is almost close from zero. So it is not a problem. A GPR can work for fresh water easily. However, to just slow down the movement of GPR, but it can go through it without any problem. On the other hand, saline water is about 3,000 millisiemens per meter. This is a very conductive environment, so the attenuation will be almost 100 decibel per meter, which will cause a high attenuation for GPR signal, so cannot go that deep. Ice is resistive. It's almost like a fresh water, very electrically resistive, and the attenuation is also close from zero. And this is interesting. Even ice, if this ice is from freshwater ice or even saline water ice, like in the North and South Pole, like in Antarctica, for example, it's not a problem for GPR because it's still resistive, because there is no mobility. It's just frozen. So GPR can work very well on having ice or snow. It can go through it and go quite deep. Clay soil could reach up to 1,000 millisiemens per meter, which is electrically conductive, and the corresponding attenuation factor is about almost 300, which is very high. So it can attenuate when you have a clay soil. It will attenuate the GPR signal. Cannot let it go quite deep. All the other materials like granite, limestone, sandstone have no problem with GPR. These are electrically resistive environment and can let the GPR go through it easily. So in general, if we have a pure water or fresh water, these are a good environment for GPR to work through them. Once we have dissolved minerals that increase the conductivity, like saline water or brackish water, then will limit the penetration of GPR. Clay in general is conductive. It's electrically conductive, it carries charges. So clay in general, especially when the clay is wet, it is attenuative. It has a high attenuation for GPR. Is an example for a field survey I recently did for using GPR, and I cannot say that I could not see below 1 meter, just 1 meter we have a signal, and below this meter we have almost no signal, just have a noise. You can see it's very noise. And I managed to get a ground truth of these measurements. We get a trench, and this signal is coming actually from a power line. You can see this signal coming from this power line, and below this power line we have mainly a wet clay. So the wet clay causes a high attenuation, which you can see there is no signal at all. This is the ground truth or the trench we did in this site, and it tells us that clay can have a significant effect on GPR. You can see that can only record noise. There is no very high attenuation coming from the wet clay. The fourth parameter, we already talked about permittivity, conductivity, magnetic permeability. The fourth parameter is the wavelet frequency which we are using for the GPR. Frequency is number of cycles per second. 1 cycle per second is 1 hertz. We measure through 2 peaks or 2 troughs. GPR operates from mega to gigahertz range. And as you know, it's high frequency will have a high shallow penetration, but it can provide us with high resolution and vice versa. Let's see some examples here. This antenna is 1.6 gigahertz to 900 megahertz. This can go to about only half a meter to 75 centimeters. And this can be used for in concrete or asphalt, very shallow investigations, like geotechnical and engineering applications. We decrease the frequency like 400 megahertz, it can go to about 2.5 meters in the ground, and it could be used for detection of utilities, underground storage tanks, or archaeological investigations. If you go lower frequency, like 250 megahertz, it can go into about 3.5 meters with depth. 200 megahertz can go to about 7.5 meters and can be used for shallow geology. 100 megahertz can go up to 30, maybe less, 20 to 30 meters with depth, and can be used for detection of water table. The lowest frequency you can use by GPR is about 10 to 16 megahertz, and it can go quite as deep as 100 meters, but only for ice. But other materials also can go quite deep, but not that deep, maybe to 20 or 30 meter depths in most of the case. For ice, it can go as deep as maybe 100 meter depth. In order to understand that, low frequency antennas like 100 megahertz or 200 megahertz have a long wavelength, like lambda here. It can provide us with low resolution, but it can go penetrate quite deep into the ground. On the other hand, high frequency antennas like 1 gigahertz or 2 gigahertz have a very short wavelength, but it can have a high resolution, which means high details, but it cannot go quite deep. So there's also a trade-off between the depth and the resolution. If you would like to see quite deep, you sacrifice resolution. If you would like to see have high resolution, you sacrifice the depth of investigation. Of course, you can use more than one antenna in the same site, low and high end frequency antennas. To show the effect of the frequency versus resolution here from these three examples, if you would like to see deeper, then you have to use the low frequency antennas, like for example, in this case, 250 megahertz antenna. You can see quite deep, but the details you cannot see very clearly. If you go for the high resolution, like for example, 500 or 1000 megahertz, then you can see much clearer, very clear, high resolution, but the depth of investigation will be shallower. Cannot, after some depths, it will just get some noises. So there's also a trade-off between frequency and resolution. So question, how far GPR actually see? It depends. It depends on the water salinity, the clay content, the frequency you are using. But these are examples from different earth materials. In general, it's really cannot go beyond a few tens of meters, like 20 to 30 meters, except in some special cases like ice, for example. Although high frequency limit the depth of penetration, but it is useful if you would like to see with high details or high resolution. Depth of investigation decrease as the electrical conductivity increases, for example, like water salinity, clay content. Also, when we have a scattering or materials like gravels, we have a lot of gravels or small pieces or small rocks will cause scattering for the GPR waves. Also, when we have a conductive contaminants, it also will cause attenuation for the GPR signal. This is materials are in the nature, you cannot control it, but the thing you can control it is, if you would like to increase depth of investigation, is to use a low frequency antenna, or you can use a high power transmitter or high sensitive receiver. This is what you can control in order to make sure that you get a high quality GPR signal. What we actually record in GPR is mainly a two-way time. This is, for example, like this hole, we have air and water, big contrast. So we have a two-way time, travels back and forth. We also record the amplitude of the GPR signal, and we record the polarity, the positive or negative polarity. This is what we basically record in the radargram, like this one. How it works again, this is a transmitter, GPR, and the receiver. We send signal. Part of this signal reflects back to the receiver. Other part is transmitted with depth and reflects back from deeper reflectors. So we end up having this trace. This is a GPR trace. The first very strong signal is going actually from transmitter to receiver directly. And then we have the second reflection here from the interface between these two media, which having different permittivities or velocities. We record these traces next to each other in what we call wiggle trace, but sometimes it's difficult to see all the traces by this way. So we tend to use a grayscale like this one, or sometimes colored scale, just to help us to see the different contrasts much easier. This is how can we display the radargram or the traces of the GPR. If we examine a GPR trace versus the velocity of the GPR signals. In the first signal we record in the GPR trace is coming from the transmitter to the receiver directly. It goes through the air. We call it a direct coupling or direct wave that goes from transmitter to receiver in the air, which is number one. This is what we first record in the GPR trace. Then after that, we record the ground wave, which goes from transmitter to the receiver, but the velocity of the first layer. So it's a bit slower. you recall, it comes surface wave or ground wave that goes directly from transmitter to the receiver. And after that, we record the reflected wave that goes, that number 3 goes down and reflects from interface and turn back to the receiver. This takes a bit longer time. This is a reflected wave and recorded later in time. Again, this is the antenna. We have a direct wave, it goes from the transmitter to receiver. This like A, that's like this one. And then the G is a ground wave, which goes from transmitter to the receiver, recorded just below it. And then we have the reflected signal goes into the earth, reflects from the interface and turn back again. Look, it's recorded in a later time. This is the some of the GPR waves it's most commonly seen in the GPR radiogram. Again, how it works, I will show this animation also. If we have a media here, 2 media, we have different velocities or different permittivities. And we have here a GPR system, transmitter and receiver. We send a pulse that reflects from this interface. We record that as a trace distance versus time. And if you do the whole survey for the study area, we got, again, all these reflections come from this interface. So we know that we have a reflector here from between 2 media here. Similarly, although if we have a cavity or utility in the subsurface, like this one, for example, and then we send a pulse. This pulse is recorded here, like this blue trace signal here, right here. And then if we continue the whole survey area over this target, then we record these blue signals right here. It takes a shape, hyperbolic shape. We call it a diffraction hyperbola, because the body here is 2-dimensional in shape or 3-dimensional in shape. So it takes this hyperbolic shape. This is how we can characterize the presence of a cavity or utility in the subsurface. Let's talk more about how this diffraction hyperbola takes place. If I have a utility here or cavity and I have an antenna here, let's see how we record this hyperbola. First, we record 2-way time that coming from this GPR reflections. It's recorded here as points. When the antenna is just above this cavity or this utility, it takes shorter time. The minimum time is just when the antenna is just above it. And then we have all of these traces taking the hyperbolic shape, and then it happens could be displayed in a grayscale like this shape. This is if we have many utilities or many cavities in the subsurface, then they will look like that, looking different hyperbolas from each target like that. If we'd like to know the exact location and depth of this target, we just go to the apex, the top of this hyperbola. This is exactly where, if we drill here, we will find this target at this location. So the apex tells us about the location of this utility or this cavity in the subsurface. Again, this is how it works. And the apex of this hyperbola is the exact location of this utility or this cavity. We call this cone or footprint as a cone of energy. It starts even ahead of the GPR transmitter. And if you keep moving, we start recording reflection. Once it hits the utility, we can have a signal here, and then keep moving on. We build up this hyperbola. When we're just above the utility or the cavity, then we reach to the apex. And if we continue moving on, we start building the other limb of the hyperbola. This is how we record hyperbolic shape from a 2-dimensional, 3-dimensional target in the subsurface. We end up having a radiogram like that, distance, meter, and time in nanoseconds. We have a direct coupling that goes from the transmitter to receiver, and we could have a bunch of hyperbolic shapes corresponding to different Earth material that have a circular shape or a multidimensional shape in the subsurface. We commonly see hyperbolic shapes related to point object, like, for example, utilities, rocks, tree roots. We also can see some boundaries or interfaces from different Earth materials, like different layers. This is what we mostly commonly see in radiogram. This is simulation showing a layered Earth. If we have an antenna on the surface of the Earth, which is a red line right here, this is an air, and this is the underground layers. You can see that the velocity in the air is much faster compared with the layered ground because the permittivity of air is just 1, and the Earth's materials have a higher value, so it goes very fast in air. Once this signal hits the interface and subsurface, we get some reflections. As you can see, these reflections come from this interface. Another part is transmitted to the lower or deeper layer, and you get reflections from a deeper layer as well. This is what we record in the case when we have a multi-layer Earth. If we have a utility or cavity, then we could have also reflections coming from this utility, especially if it's a buried pipe or landmine. If it's metallic, we have a very high, strong reflection. If it is made of concrete or other earth material, can get good reflection, but not as strong as the metallic ones. So this is how we record the presence of a cavity or utility. Also, what affects the reflection is the content of this utility or cavity. If it's air or water or any or other soil materials, also have an effect on these reflections. If we have a scattering, for example, this is if we have a irregular surface, for example, not a horizontal interface, or if we have a rocky soil that have many small rocks, or have a clutter coming from a buried object, this will have a bad reflection on the quality of the GPR signals. We have more scattering. You can see a signal is scattered because if we have, for example, if we have gravels or small rock pieces, it will have a bad reflection on the GPR signal. But this is a simulation, shows how it looks like when we use a GPR. GPR could be measured in different setups, like, for example, a common offset, which is distance between transmitter and receiver is constant. So common offset is commonly used. You just move the transmitter and receiver along the survey line. You can also use what's called common midpoint measurements. CMP is where you move the transmitter away from the receiver, and you got the reflections from the first interface between the first and two layers. This is commonly used to determine the velocity of the first layer, which is required to determine the depth of investigation. We can also use GPR between two boreholes. We put the transmitter in one borehole and the receiver in the other borehole, and measure the velocity or between the two boreholes and get the details between information about the materials between the two boreholes. It's called it can be used for mines or between the sides of walls or many other applications. So we end up having this radiogram that shows distance versus two-way time in nanoseconds. In order to transform or convert this two-way time into a depth, we need to know the velocity of the subsurface. Air is constant, or water is constant velocity, but in the Earth, it's very heterogeneous. So velocity could be varying very significantly with depth and distance. So it is not easy to determine the velocity. There are many ways to determine the velocity. For example, ground truth, where we know a specific target in subsurface, how deep this target is. Or if we use a CMP, common midpoint, or WAR, which is a wide angle reflection and refraction, or we can use hyperbola matching. I will explain each of these methods for estimating the velocity. If we have a target in subsurface with known depth, what we can do is just to measure the two-way time, so have a signal goes back and forth, and knowing the two-way time and knowing the exact depth of this target, then we can easily calculate the velocity. We already know the depth, then the two-way time divided by 2, you can just get the velocity of the subsurface. But this is not very common to find a known target. If you have a known target, this would make your life much easier. But if you don't, you can also use a CMP, which is moving the transmitter and receiver away from each other, like this way. And from these measurements, you can calculate the velocity. You can get the velocity spectrum like this one. You can just calculate from this direct wave and reflected wave and refracted wave, and you can easily get the velocity for each of these reflections. So this is quite similar to what we also do in seismic methods. Hyperbola matching, when you have a hyperbola in your radiogram, you can make use of it. You can have this fictitious or artificial hyperbola. It's available in many software. Try to fit this hyperbola. We can sometimes call it a ghost hyperbola or artificial hyperbola. When we fit it, then the software can calculate the exact velocity from the top of this hyperbola. This is one way. Another way to determine the velocity from having hyperbolic shape in your diagram. Basic GPR systems is very simple. We have a control unit and display unit that sends signal the transmitter, like this one. This signal goes into the ground, have a reflections that from the receiver antenna that goes again to the control unit and can be displayed like in this display. So it's a very easy process in the field, can be done by one person or two persons to do a GPR survey very quickly. Most commonly, when we do a distance mode GPR system, we use a wheel, whether a single wheel, 3 wheels, or 4 wheels. The wheels is not just for convenience, it is also used to measure the distance. As the wheel moves on, we can cut to how far you cover. And this is recorded if you have a GPS system, can record the location. But before you start any survey, you need to calibrate this wheel. You have to have a meter and do a calibration, tell the system, for example, this is a 5 meter or 10 meter. And it's recommended to do this calibration on the same soil where we are going to do the GPR survey, and move also by the same distance. You don't have to be very fast or very slow, just to move by the constant movement or steps, so you can have a good recording for the signals and have also good stacking for these signals. GPR antennas are very length of the GPR antenna varies based on the frequency. For example, the lower frequency, like 250, 25 megahertz antenna, which is very low frequency antenna, could be as long as 4 meters because the wavelength of this antenna is very long. If you go to 50 megahertz antenna, could be like 2 meters. 400 megahertz could be just 1 meter. If you go to 100 megahertz, could be just half meter. If you go for higher frequency antenna, 500, 1000, could be very small antenna. There's also, as I mentioned earlier, there are trade-off between penetration depths and resolution. Most commonly, GPR goes from 1 meter up to 50 meters, could be maximum depths can reach with GPR. And these are different antennas from 1000 megahertz antenna up to 12 megahertz antenna that can be used for many applications. Usually the very low frequency antenna could be used for geology. 25 and 50 megahertz could be used for geological investigations. 100 megahertz can be used for geotechnical and sinkhole detection. 200 megahertz could be used to 100 and 250 for utility location. 500 megahertz can be used for, and 250 also can be used for archaeological and forensic studies. Higher frequency antenna like 1000 can be used for concrete and road inspection. Each antenna have a range of frequencies, but the maximum amplitude of this frequency is called the central frequency. And this is the frequency we name this antenna. We say this is 100 megahertz antenna or 400 megahertz antenna. Is just the maximum peak amplitude of this frequency called central frequency. Usually high frequency antennas are shielded. The shield is just to protect the antenna from external noise, while low frequency antennas like 50 or 25 megahertz are usually unshielded antennas. Is an example of different central frequencies from 12 megahertz up to 200 megahertz antenna. You can notice that low frequency antenna have a long wavelength, deeper penetration, but low resolution. You can see, for example, that 12 megahertz can go quite deep, but the resolution is very weak and difficult to characterize what are these materials is. But if you go to high frequency antenna like 100 or 200 megahertz antenna, it has a shorter wavelength, low penetration, cannot go quite deep, we are slightly attenuated after some depths, but can provide with more resolution, more details. You can see here, characterize these materials and interpret much easier compared to the low frequency antenna. So there's also a trade-off between the frequency and depth of investigation, or resolution and depth of investigation. Most commonly, when you have a one unit that have transmitter and receiver, we call it a monostatic antenna. While when you have a separate transmitter and receiver, we call it a bistatic antenna. GPR works by generating a signal in time or frequency, send this signal to a subsurface, and then received signal goes to analog digital converter, and that's recorded and then displayed in the screen, like this system. It's a very simple system. As I said, it's a one-man show system. You can just drag the antenna behind him and have the control unit and can just record these GPR radiogram and interpret after that. Acquisition can be done in different environments. Is myself doing a GPR survey in an area for detection of cavities, and this is from my home country in Egypt. Also, you can do a grid of GPR survey that can go different directions for more details, and you can see a different depth time slices or depth slices with more details about the subsurface. Applications GPR is very wide. It can be used for utility detection, pipes, foundations, can also be used for landfills. It can be used for different layer, reflect between different layers, contamination, in contaminants that have that affect the water, or can be also for detection of groundwater table. I said groundwater table is very easy to recognize because the materials above it is very dry and below it is very wet, so the big contrast and permittivity. So you can see easily the groundwater table. A limitation of GPR, I said, is when you have a saline water, it doesn't go very deep, but sometimes it could be useful to discriminate between fresh and saline water, like in a coastal area. In saline water, the GPR signal just attenuates, while in the fresh water can go quite deep in it. So you can easily determine the interface between saline and fresh water, like in this case, saltwater intrusion. It can also be used for sinkhole detection, log glacier, archaeology, underground tanks. When doing GPR in above ice, it can go as deep as hundreds of meters, which is very extreme cases. It's not very common, but this can be done, like in Antarctica, for example, can go quite deep. A very interesting story has happened in Greenland. What happened, that was a military airplane called the Squadron. This airplane falls into a lake in Greenland, and happened that in 1942. And after 50 years, they decide to locate this airplane. Where is this airplane? So they wait in the winter time and did a GPR survey above the snow. It can see the airplanes about 85 meters in depth. They managed to get this location of this airplane by this GPR survey above this lake. And the question, how can we get this airplane out of this snow? So they decide to dig deep down, 85 meters, very deep. And they managed to find this airplane, which is a military airplane. What's interesting, they cut it into pieces, and they took this wing he's taking out. And what's very interesting is that he managed to assemble this airplane again and did to fly one more. Very interesting story to share with you. It's not very common, but it's very interesting to share. Also, GPR could be used for forensic study, for criminal investigation study. It is a very useful tool. Many police use GPR now as a tool for crime investigations. It can detect the buried bodies or drugs or weapons in the subsurface. The idea is just to locate any disturbance in the soil. So this, for example, a GPR survey, the areas of significant disturbance is where the persons have digged into the ground and changes the soil. When he dig the ground or the soil and turn it back, it will not be the same as the original soil. So can he see a disturbed soil? This disturbed soil that tells us somebody digged here and buried those two bodies in the subsurface. This is one way to use GPR for detection of forensic studies. Again, also for weapons, can have a hyperbolic shape. For a stolen safe, can also have a reflection that can tell us we have a metallic material here or a safe here. GPR also can be used for pipe and barrels in detection. You can see here barrels or pipes. It can also show it into a cross section or through depth slices or time slices in this case. Again, this is a buried tank detection or underground storage tanks. It can be also used for utility detection like sewer, like gas and water pipes, electrical and communication cables. All of these can be detected by GPR. Again, as I said, in archaeological studies can detect the graves or tombs very easily. GPR is very useful in archaeological studies because the site, once it goes inside and outside, does not make any digging or change in the site. This is very important for archaeological investigations. It can be also used for geological stratigraphy. Like in this case, we have here a cross-bedding in the sand dunes. Again, for deltaic areas, can characterize where are the sand. Of course, the clay here doesn't show much signal, but you can at least know the contrast between the sand and the clay layers. Can be used for water table because there is a contrast here between the dry and wet, so the water table here is very clear mapping. For landfill detection, sometimes we have a landfill and have a contaminants in this landfill. These contaminants could leach and affect the water in the subsurface and cause a contamination. So this survey for the landfill area causes a contamination that goes with the water here. This survey GPR showed that these contaminants are very conductive, mask the GPR signal because they have a lot of electrical conductive material. So what happened after 5 years, they did another survey, the same area at time lapse to check if these contaminants have been removed or not. So after 5 years, they said that same survey, they found out this area have been cleaned from contamination. You can see here a strong reflection of GPR. However, there are still residual contaminants in the other site right here, so need to be removed. So it's a good follow-up technique for the detection of different contaminants and make sure that they are all cleaned or not. It can be also used for granite quarry mapping to check if there are any fractures or faults in the granite or limestone. It can be also used for limestone cavities, like dissolution cavities in limestone. Again, for sinkhole detection, like these cavities, a sinkhole could be dangerous, could have a collapse if we would not detect it or degrouting it. Again, here for cavity detection, this is especially if you have a surface, it's better to start from this point and go on to check if the site have any more cavities or not. Salt mine, dry salt have no problem with GPR, but when you have a wet salt, then to be extremely conductive, so you cannot hardly get any signal. So you can make use this plank that tells us we have some water here with this salt. Mine shaft detection also can have a hyperbolic shape. Landmines detection, especially the anti-tank landmines, big in size, can be detected by GPR. Unexploded ordnance detection, UXOs like rockets or bombs that did not explode, just still there as a hazard. So we need to detect these UXOs to clean it, as can cause a harm for persons if exploded. Again, for freshwater bottom lake, we have a bathymetry to monitor the depths of the lake. If a freshwater lake, have no problem. You can put the sensor here on a boat or drag it behind you, and then you can get the depths of the freshwater lake. As you can see, it's very clean here. So freshwater have no problem with GPR, but saline water will have a limited depths of penetration. Also get the ice thickness. If you survey and the ice here, and they get also the thickness of the water, deep water. You can even see here that a trunk of a tree have a hyperbolic shape right here, and then you get the thickness of the deep snow. Foundations can detect the foundation of a building, and if there are any pipes here, it will show up as hyperbolic shape. Tunnels, if you have big tunnel like this tunnel, for example, here to conduct a survey, it will show that tunnels have a broad hyperbolic shape, while if you have a cables, have a narrow hyperbolic shape. You can discriminate between them easily. Road beds, if you would like to check the quality of the road, if there are any fractures or fillings or cavities within the road, you can just mount the GPR antenna behind the car or in front of the car and scan the road. This is very useful to detect if any fractures or cavities or sinkholes in the road. Also, for railroad bed mapping, if you detect any cavities or ice wedge or any material that have a substance that might cause a collapse or a danger for the train. Recently, they put many antennas below the train with different frequencies and different pairs of transmitters and receiver. And just you can put many transmitters and receivers just below the train that cover a wide range of frequency from 200 megahertz to 3 gigahertz to detect both the shallow and deeper targets, to detect if any fractures or any cavities that might cause a problem or an accident for the train. For geotechnical engineering investigations, they tend to use a high frequency antenna to map the rebars to make sure the rebars are okay. Good rebars have a strong reflections, while if you have a corroded rebar, have a water in it, this corroded rebar will show up as a weak signal. You can have a very weak signal here that's coming from the corroded rebar. So you can discriminate between the fresh rebar and the corroded rebar using GPR. This is a high frequency antenna. It's about 1 gigahertz antenna. Airborne radar can be mounted on airplanes that can fly and cover very large distance, like this Greenland, for example. It can be also map the a desert area. For example, is an airborne radar, 40 megahertz antenna. It managed to go as deep as about 70 meters in depth. Take the water table here. This is a dry sand, and this is a water table. So this is very useful for scientists to study the past hydrological conditions in Earth's desert and assess how the climate change. This is a very good investigations for desert area using an airborne radar. You can also use GPR for gas and water main pipes delineation. You can make a cross section or have depth slice show how deep these pipes are. You can also plot it in a three-dimensional visualization. You can show GPR either 1D single trace or a two-dimensional cross section. For two-dimensional vertical cross section, like when you cut the cake vertically, this is a 2D vertical cross section. And you can also show it in 2D horizontal depth slice, for example, as if you are cutting the cake horizontally at different slices. So you can see this depth slice, or you can plot it in a 3D visualization, 3D volume, like a cube. These different ways of plotting GPR. This is again, if you do a multiple 2D GPR, or go 2.5D or 3D, and you can also see a depths or time slices at different depths, and you can combine them in a 3D visualization like a cube. You can also acquire 3D and a 3D acquisition, or you have many pairs of GPR transmitters and receivers in the same system. We have many transmitters and many receivers, like 16 to 31 channels, and you can acquire a true 3D GPR that tells us about the main utilities or the archaeological studies in this area. You can also mount the GPR on drones, which is a new trend in GPR. You can mount the antenna on a drone and let the drone fly. It can also follow the terrain, go up and down following the terrain. It's a very interesting way to fly. It can be used over a lake, can be used in a high vegetation area like forests. Can also use a mountain area where it's not accessible for man to go there. Also can be used for unexploited ordnance, landmined areas, which is very dangerous to walk in them. This is an example here for how can use a drone for GPR investigations. This is the drone itself. Can mount the GPR antenna. You can see it. This is a low frequency antenna, and the user here can control the path of the GPR, how it goes back and forth on advance. Can also record the data in real time or store it and then process it later on. So this is how it looks for the GPR antenna flying. This is another antenna, higher frequency antenna, and they mount it on the drone. And the drone contains an altimeter to measure the elevation, and data logger to store the data. And this is the altimeter and the GPR antenna. So these are the components that measured, could be measured in real time, and this is how the real-time data can go directly to the person in charge, and he can process the data and try to interpret. Here's how the drone flies with the GPR antenna, and this is the path it follows on advance. And as you can see, this is very high vegetation area. It's very difficult to go through them on the person would like to do a survey. To be difficult to conduct a ground survey using GPR in this forest area. And then after that, they process the data and come up with interpretation. And also you can follow terrain here, up and down, depending on the terrain. And this is the survey line. And this is a low frequency antenna, a bit heavier. It can be also connected to the drone. And the same story, also can flies and cover large area. Another survey here done over a lake. Again, they can fly this antenna over a lake and get the depths of to this freshwater lake. And this is the GPR antenna flying over the lake. Can go with a very low altitude above the lake. And see it can fly over the water here, and again have also the altimeter and the storage, data storage logger and GPR antenna, and it can cover this lake very quickly and send the data in real time, and then could be interpreted after that. It's very simple, and encourage you guys to try. If you have available to you, you can try this survey. It's very quick and easy, and this is a new trend in the new future for GPR. You should consider also a source of noise. There's many sources of noises, like, for example, the cellular phones, two-way radio, radio and TV stations. All of these works in the same frequency range of GPR. So these could contaminate. We record in the receiver. The receiver will not only record what's coming from the subsurface, will also record these signals coming from these sources, so to contaminate the GPR. It's not recommended to do a GPR survey close from a TV or radio station. It's also not recommended to use a cellular phone, two-way radio when you are conducting a GPR survey. These radio stations or radio noise will affect the GPR data. You can see these these noises are coming from these radio stations, TV stations. Called radio frequency, and you can detect it when you can see that it starts even before the GPR measurements start recording, and after that. It means that it has been there for all the time. This is kind of noise that you need to avoid. And GPR, we have, if you can analyze this GPR section, we have a noise that's before starting the GPR measurements, and we have a data while measurements of the GPR is done. And then after that, we have a noise after which the signal have been attenuated. The depth, this depth here is called depth of penetration, maximum depth of penetration. This is the depth the GPR signal amplitude falls below the noise floor. So you cannot have any signal here. In order to improve this depth of penetration, you need to make a lot of measurements or stacking for GPR. When you stack the GPR data, then you can improve, you can a little bit see a bit deeper and can characterize some targets with depth. So the only way to do that is to do a lot of stacking. Stacking here, that if you have only one signal, the signal to noise ratio here is not that good. You have a lot of noisy data, random noise. If you make a lot of stacking, 4 or 8 stacking, then we get rid of this signal, improve the signal to noise ratio. So the noises here are removed because these are a random noise. So for example, here, if you have 2 stacks only, you still have a lot of noises here, but you have like 8 or more stacks, then you can have a strong signal, and the noise here have been canceled each other. So it's recommended to do a lot of stacking. This can be done when you move slowly. You don't have to move very fast. The more slowly you move, pushing the GPR antenna, you can do a lot of measurements and stack them, and this will improve the signal to noise ratio. Just a very few GPR processing steps is a static correction, where you can move this zero before recording the GPR. There is a time that have no signal. Then you just move this zero time zero up to its actual location. It's called static correction. This is very easy to done by any software. Also, background removal, which is a low frequency noises. It looks like a banding. This banding right here, you can remove it by using a filter. It's called DWOW filter. Then you can clean the GPR section. For example, this banding right here, if you apply this background subtraction or removal, then it's no longer there. Similarly, also have a lot of banding here. That's a low frequency noise. You can, if you apply this filter, you can remove. But you have to be careful, because sometimes you could have actual reflectors. If you apply this filter, it can also remove any horizontal reflector, can remove the noise and the signal. So you need to be careful when applying this filter. Again, using the gain. Gain is one of the important steps for data processing. Actually, what happened that the GPR signal attenuates as it goes with depth. So we need to adjust that or counterattack that by adding a gain with depth. So increase the gain function with depth to improve the deeper signal. Instead of being very low or very weak, you reconstruct here the signal to be a stronger signal. So choice of the gain is needs some practice. Here, for example, the gain is very low. You can hardly see any signal. This gain is too high. Actually, it's not recommended, but this one could be the right one. How do you know the right gain? When you start seeing the background noise with depth here, then it means that after that you will just amplifying the noise, not amplifying the signal. So when you start seeing this background noise, it means that this is just the right gain you can use. One of the steps also is the velocity estimation. When you have a hyperbolic shape, you need to have this ghost hyperbola or artificial hyperbola to apply it and then calculate the velocity. The ghost hyperbola or the artificial hyperbola depends on the permittivity of subsurface. Could be a wide angle or small angle depending on the permittivity of subsurface material. Choice of the velocity is very important. We have here, for example, in this section, a small hyperbola and a large hyperbola. If we try to fit this small hyperbola, for example, here, we got the velocity of 0.1 meter per nanosecond. Then based on the geology of the study area, you can tell if it's a sand or moist sand. You can interpret it based on the geology of the materials of subsurface. If you try to fit the lower one, you found out that the velocity here is 0.3 per meter per nanosecond. Actually, this velocity is the air velocity. So this tells you that this hyperbola is not coming from a subsurface. It's coming actually from the outside in the surface. It's coming from the air. So the antenna just hit this building or this tree, and we got this large hyperbola. So you need to be careful not to apply this velocity of this large hyperbola. For example, here when we're fitting this hyperbola and this fictitious or artificial hyperbola, we got the velocity of 0.116. This is basically the velocity of limestone or moist sand. Again, you can interpret based on the geology of the study area you have. A choice of the velocity will affect the depth section. So if you select a wrong velocity, the depth will not be correct. For example, if you have a 0.01 meter per nanosecond, the depth is from 1 meter to about 4 meters. But if you apply a velocity of 0.14, the depth will change, be about 1.45 meter up to about 5.5 because you use a higher velocity. So if you apply, for example, here this large hyperbola, which is 0.3 meter per nanosecond, which is for light, which is for the air actually. If you mistakenly apply this velocity, then the depth will be about from 3 to about 12, which is not actual. Because you applied a wrong velocity, incorrect velocity would have a reflection of the depth and the interpretation will not be correct. So you need to make sure that you apply the correct velocity. Done with the basics now. I'm gonna go through very quickly with a case study, which I used GPR for detection of cavities and sinkholes. This was done in Oman, where we have acoustic features. We have limestone, which have a lot of dissolution, cavities, and sinkholes and cavities. This is a very serious problem. Sinkholes and cavities could be a hazard for residential area underlain by limestone. It will cause structural instability and might cause a collapse of buildings. So the limestone in this area have a lot of cavities, similar to Swiss cheese. In the neighborhood of the study area, there was a famous sinkhole that's called Bima or Hawat Najm sinkhole. It's about 30 meters in diameter. It's a touristic area, but this area have a lot of sinkholes and cavities. The objective or definition of the problem there is that people living are fishermen living in this coastal area in above limestone, and the water of the sea here goes within the limestone, cause cavities and within this limestone. And this is very dangerous because it might cause a collapse for the rocks and could affect the lives of those people. So there's another area have been selected by the authority that's in the neighborhood about 2 kilometers from this site. So we have been asked to examine both sites, the old site where the people are living and new site where nobody there, and see which one is suitable for living with those people. The geology of the area is mainly limestone, conglomerate, and marl. The area is dominated by cliff, like a cliff, coastal cliff like this one. The elevation of this cliff is from 5 to 10 meters above the sea level. There are many fractures within these limestones that cause a dissolution from the seawater. I used at this time GSSI system. I used 2 antennas, 400 megahertz and 270 to account for the deeper and shallower investigation, high frequency for shallow and 270 for deeper one. We managed to go to up to from 3 to 7 meter depth. The 270 antenna, we managed to go about 120 nanoseconds, and 400 megahertz, we got time about 60 nanoseconds. I used 1024 samples to get a high resolution samples, and about 40 scans per meter to account for the stacking. How many 40 scans a scan can stack these 40 scans to get a better signal to noise ratio. The director constant for limestone is 8, so I use this value for calculating the velocity. This is what we call old Wadi Shab area. We have residential area. We have only 2 roads in the where we have buildings just next to you. These are my students when we conduct this survey. So we have 2 profiles here within this area. On the other area, which is there's nobody there, it's open. So we did a lot of profiles, like 9 profiles there, with 15 meters between each profile. It's the cliff or the elevation also from 5 to 10 above sea level. And this is, you can see this surface is almost flat. So we did the survey in this new Wadi Shab area. In the old Wadi Shab results, after processing the data, we can see here a very broad hyperbola. You can see this. When you calculate the velocity of this broad hyperbola, we found that it is due to air wave, which means that it's coming from outside the earth, coming from a tree or a building that have this. So don't get confused about this broad. You can see that we have a sinkhole here or a cavity. Actually, this is an air wave because we calculate the velocity of this hyperbola and found that is of the air. We can also see this is coming from reflection from the tree or a building. We can also see some fracture zone in the radiogram, right, in these areas. Our maximum depth of investigation was about 6 to 7 meters. After that, the signal get attenuated. This is for the 270 megahertz antenna. To explain this airwave reflection, if you have here antenna transmitter, it hits the tree and turn back, or the building turn back, and then we can see that this broad hyperbola. And if you calculate the velocity, it's 0.3 meter per nanosecond. It is for air, so we know that this is from outside, not from inside the Earth. You also have a light pole, can also get a similar reflection for 0.3 meter per nanosecond. You need to be careful with any surface feature that could cause these reflections. This is another profile. You can see here a very linear feature, similar to the airwave reflection. And we verified that it's also velocity is also 0.3 meter per nanosecond. This is actually when we have a building like these houses, and we have this linear feature from the GPR signal hit this building, can see this linear feature, and the slope of it was 1/c, which c is the velocity of light. So moving away or towards the surface, object may produce this linear event. Again, you can see some fracture zone in the near surface here. This is another profile for the 400 megahertz, which show higher resolution, but can also can go as deep as 4 to 5 meter only, because this is a higher high frequency antenna. But you can also still see the airwave reflection, but you can see also a very interesting feature which is called ringing. This ringing actually is again coming from small metals, a wire near the surface. Keep bringing this small metal acts as an antenna and show this ringing. You can also see some fracture zone here in the near surface. The depth here is about 4 meters, after which the signal get attenuated. This let me explain this ringing. It will have a piece of metal. It's get energized by the GPR transmitter and acting as a radiating, and keep just going back and forth and shows as a ringing like this one. So this piece of metal or manhole close from this GPR measurements, it can cause this ringing. It is very strong response from metal or near surface feature like manhole. So don't get confused by this stuff. It's not coming again from the ground. It is from the surface features. If you go to the new Wadi Shab area, which is the open area, we will no longer see any air wave here because there's no buildings or trees, just a clean area. You can see only many dozens of dissolution cavities, many hyperbolas here corresponds to dissolution cavities in the limestone. The depth here was only 3 meters, after which the signal get attenuated because of the seawater. The seawater here, moisture of the seawater or residual salt within the limestone cause high attenuation for GPR signal. Again, you can see a lot of dozens of hyperbolic features corresponds to these cavities or small cavities from the limestone. This is a surface feature, but reflects the subsurface. Again, you can see many hyperbolic features here, corresponds to small cavities. This is a very interesting feature. This is again a dissolution cavity, but I can see here a big hyperbolic feature. This is from this profile here. So when I was in the site, I went all the way to this node here, close from the sea, and I had a chance to have a look what's below this profile. So what I found that there is a very big fracture zone that shows this hyperbolic feature. This is a survey line above it, and I was lucky to find this land area to see this hyperbolic feature coming from this reflection from this cavity. We can also here see a surface feature like this surface, a strong reflector here. It might be interfaced between two media having different velocities, different permittivities. We can also see here some strong reflectors here might correspond to a fault zone, because I have seen the surface is a fracture zone here. Again, the same feature also in different profile here, very strong reflectors, might be due to a fault zone or an interface between two media. A very interesting here linear feature also, but below it there is a possible cavity. You can see hyperbolic feature here. It's a possible cavity. This profile is done at the edge of this area. We can see a lot of hyperbolic feature, like dozens of dissolution cavities, and this is a corresponding edge of this plateau. You can see many cavities here, and I'm standing here at a scale, and these small cavities causes these hyperbolic features. So to summarize, GPR is a high-resolution near-surface imaging tool. It uses reflected high-frequency radio waves to image the subsurface. The reflections coefficients depends on the permittivity of the ground, and permittivity is very sensitive to moisture content. It's a strong trade-off between penetration depths and resolution. Frequency is a key survey parameters. Remember to consider ground surface, primary reflectors, and multiples, and diffractions, and ringing. Two-way time sections may be converted to depths using the right velocity. If you use a wrong velocity, it will have a different depth, wrong depths. Many similarities with seismic data processing. If you are familiar with seismic data processing, almost apply many of the seismic data processing steps. It's a great advantage if it is of GPR is that it is non-invasive and it's cost-effective. If you can cover large area in a very short time, have a high spatial density of measurements. Under that condition, GPR can provide the highest resolution subsurface images compared to any geophysical method. It can show a vertical and lateral resolution on a centimeter scale. It can locate metallic and non-metallic utilities. GPR works best in dry conditions. It can also still work for fresh water, but not in saline water. There should be a contrast between indirect permittivity to see the targets. This is the contrast, the reflection coefficient. It's not appropriate for very small and deep targets in electrically conductive environment like clays or saline groundwater or mineralization. You must know the geology of the study area before you specify GPR, or you may be wasting your time and money. That's all. I would like to thank the EAGE for inviting me to present this webinar. Also would like to thank Sensor Software for sharing some of the materials I used in preparing this webinar. Finally, I would like to recommend this book chapter. It's called Ground Penetrating Radar in a book called Near Surface Geophysics. This chapter is very interesting to read. It's by Peter Annan. Thanks for your attention. If you have any questions, please feel free to ask. Thank you.
Thank you so much, Dr. Hesham, for this amazing talk. To the attendees, if you have any question, you can turn on your microphone and ask directly to the instructor. Please go ahead.
You can also write down, send me this question. I can try to answer it.
Yes, for sure.
If there's no questions, you can always email me or send the questions to Maria, and you can email it to me, and I can turn back to you and answer the question through email. It's also another option.
Yes, for sure. So if we don't have any questions from the participants, I can also share Dr. Hesham's emails.
Hello, Dr. Hesham.
Oh, there is a question. Yes,
Hello.
please go ahead.
Go ahead.
Hello, Dr. Hesham. Thank you for this wonderful presentation on GPR and application in various subsurface studies. So I have three questions. The first is that as we read about GPR is that EM velocity is dependent upon the RDP. The direction depends upon the conductivity and frequency that we use. So it is also true that if there is a high water content in a soil, then it will impact both RDP and the conductivity, right? So is there any relationship between RDP and conductivity? Can we calculate conductivity directly from the RDP?
From what? Can calculate conductivity from RDP? What you?
Like
I just,
relative dielectric permittivity. Yeah. Can we calculate conductivity directly from RDP?
I think
because
no.
both are related. Both are very positively. Yeah.
Yeah, sure. Yeah, but I don't think there's a direct relationship between the permittivity and the conductivity. They are two different parameters, but I don't think there's a direct relationship because permittivity affects actually the velocity, how fast or how slow is the GPR penetration. While conductivity is much related to the attenuation, how fast, how high is the attenuation, or how low is the attenuation. So they affect the GPR signal in different ways. One affects the velocity, which is the permittivity. Other one affects the penetration depth, how deep it can go, or how high the dissipation. And so they affect it in different ways. If you can see in the beginning of my lecture, I showed an example showing the dry granite versus the wet clay. So dry granite, for example, it is dryness or wetness affect how fast the GPR velocity go through them. And the material itself, resistive or conductive, affect the dissipation or attenuation of the GPR signal. So they affect the GPR in two different ways.
So no, what I was thinking is that if there is a soil mass, if we increase the water content of that soil mass, it will impact both RDP and conductivity. So there is a positive correlation between these two parameters. So can't we devise a correlation between these two parameters and directly correlate it?
It might be if you increase the water content in the soil, it will definitely affect the GPR, but the effect will be one of the effect is the slowness of the GPR, how slow it will go once you have more water content. This will affect the permittivity, so it will affect the slowness of the speed of the GPR wave. And for the conductivity, it will affect to be high conductivity, so it will affect the depth of penetration, how deep it can go, because it will be attenuative. I'm not sure there is a relationship that correlate them, but you can write that and come up with even a side characteristic relationship, but there's no general relationship that connects them. You can apply directly.
Thank you for that. And my second question is that you talked about hyperbola fitting to calculate the velocity. So like that hyperbola fitting gives the average velocity of that depth. So do you think that it's a right process to calculate the velocity? If you want to know the absolute velocity of that particular depth, then do you hyperbola fitting is a right choice for that?
Yeah, if you have more than one hyperbola, it's better to detect the one at shallow depths and the one at deeper depths. So because they correspond different materials, probably different earth materials. But you have only one hyperbola, then you can have, this is the only choice you have. You can apply because this is an average velocity of the media. But if you have more than one hyperbola, it's better to try to fit each one of them. And the deeper one will be more useful because it's coming from a deeper depth. That's useful if you have more than one hyperbola. But if you have only one hyperbola in the site, then you have no choice. This will be just an average, not an accurate, but it's an average velocity for the site.
And you also talked about cavities. So those cavities could be water filled and air filled. So can we just look at the hyperbola signature and can we just say that which hyperbola is showing the water filled cavity and which is showing the air filled cavity? Can we say that using by seeing the hyperbolas? Hello.
An air or water is from the sequence of the phase, white, black, white. If it is this sequence of phase will tell you if you have an air or cavity, because when you go from low permittivity to high permittivity, there's a contrast. So monitoring the phase, which is if you from a grayscale to be white, black, then from this phase, if you use a different color scheme, you can also monitor the phase. So monitoring the phase will tell you whether you have an air or water, because if it's an water, this is a much higher, that's an 80, permittivity is 80, while the host material will be less than 80. So it's going from low to high, while in the air, it is much less compared with the surrounding materials. So it's going from high to low. So the phase of the signature of the GPR will tell you whether there is an air or cavity or water. Sorry.
Okay, thank you for those answers. Thank you very much.
You're welcome. Thank you.
Thank you, Abhishek, for your questions. Any other question from the attendees? It seems that we don't have more questions. Dr. Hesham, thank you so much for being here today. What I'm going to do after this meeting is to upload the recording of this video into our YouTube channel for sure. Then I will be sending you all an email, and I'm also going to share through that email Dr. Hesham's email address. So thank you so much. Again, it was a pleasure to have you here during this amazing webinar, and we hope that you can join us in our future online sessions.
Thank you. It's my pleasure. Thank you very much. Thanks for attending the lecture.
Thank you. Thank you. Thank you all. Thank you. Bye-bye.
Bye-bye. Take care. Bye.